So I'm up first. You'll get your dose 2 of talk about water. Different scale, different kind of an issue, really. And then later this morning, Diane will talk about, let's see, it was Da Vinci. I know that, Beyond the Last Supper. And maybe she'll touch on the fact that, talking about connections here, Da Vinci was somebody who wrote extensively about water, about the art of water. He was fascinated with vortices and spirals and things like that that you see in water and turbulence. He even proposed irrigation schemes for areas of Italy that didn't have water. So certainly connections there. Maybe she'll talk about art or something else there. You're probably going to have enough after I get through. Let me talk a little bit in the same way that Drew did about who I am and kind of where I come from before we get into this. I'm a civil engineer by training, but I've always been interested in the water. You think of civil engineering, you may think a lot of buildings and bridges and roads. I've always been more in the water environmental side of civil engineering. But along the way, I've worked quite a bit with other types of scientists. When I was doing my PhD work, my project was out in Los Alamos. And I was actually in an environmental science group. But we were interested in the transport of the radionuclides that have been strewn all over that mesa top up there and buried here and there, how they transport off the mesa. Okay, so that's a problem of environmental issues, but also water and how it moves in the environment. So I've always worked with these other types of people. And so I've always been a little conflicted and maybe torn between what my identity really is. Okay, there we go. Whether I'm a civil engineer or a scientist, a hydrologist, and really I'm some kind of combination of both. And the neat thing is now and then you can blame problems on the civil engineers and pretend you're a hydrologist and vice versa if you have to. But certainly, we don't have to answer the question, what's a civil engineer doing talking about water? We've been doing water since day one. And in this country, there's an ASCE, American Society of Civil Engineers. The people who started that were working up on the Croton Aqueduct in New York City. Do you all know, have you heard of the Croton Aqueduct? Okay, some people live right there, right? That was the first water system, real water system to bring water into Manhattan. And that was when this group got started. Now, it's not the first time people, didn't call themselves maybe engineers at the time, were interested in moving water around. That's been going on for thousands of years. This is a picture. I'm going to be there next week in Segovia in Spain, where there's this 2,000-year-old aqueduct that's been well preserved. They have done some work on it to keep it looking like this. But certainly people, for as long as we've been civilized, have been interested in improving, our way of living. And to do that, a lot of times you need to bring in more water. You want to grow more crops. You may like to live somewhere, but it's a nice climate's good, Southern California. Unfortunately, there's not a lot of water there, so you bring it in, right? But through the interactions with other professionals and a realization, really, in the last, maybe just a few decades, maybe 50 years at most, the Earth is this complicated, interconnected system. And civil engineers aren't going to do a good job of solving our problems if we're working alone, okay? Now, the hydrology is connected to, as Drew mentioned yesterday, the ecology, the weather. It's all connected, and a lot of times it's social issues and constraints that really matter in the end, okay? Thus, in fact, they've had a hand in creating some. Those civil engineers, right, has had a hand in creating some of our own problems. So, see, I can say they now and then. I am a member of ASCE and a licensed engineer and all that, too. Okay, let's see. I wasn't educated in a place like Lafayette College. I came from University of Maryland, University of Penn State University, big technical schools. So I've been here for a little over 10 years, and what we pride ourselves on is this engineering in a liberal arts environment, right? Which is very unique. There are not many places like us. It's something we should capitalize on, and we do. And so I'm still maybe figuring out what that means. But I guess if I'm known for anything on this campus, It's that I have done my best to try to do real on-the-ground projects with my students. That's the way I motivate them. That's the way I make connections in the real world. So I do a lot of that, real community-based projects. Try to do projects with real constraints, real clients, real money. Sometimes that's very difficult to do, within a semester or a year. But I try to make that happen, and then to try to actually build something, right? People get really excited about that, not just engineers. And you'll see later, I'm working with lots of people who aren't engineers. And the other thing that I always try to bring out in my classes, no matter what they are, is this idea of sustainability. Now, maybe this is a catchword of the day, but I feel like this is a principle that's been around forever and isn't going away. We may call it something else in 20 years, but sustainability is key, and it's encoded at this point in our code of ethics as civil engineers. So it's something we have to always have in mind, and it sort of affects everything we do in some way. Just a few pictures of what kinds of things I'm talking about. Well, this is the freshman engineering class. I wanted them to this is 4-week blocks of time. They rotate through civil, chemical, electrical engineering. I wanted them to actually do something, try it, see how it works. So what we did is we built these roofs on the back of AEC over here, the Copian Engineering Center, collected rainwater, tried to figure out how we could filter it, avoid the pigeon poop that might show up the first time water runs off that roof. So they had to sort of engineer it a little bit. And then by the end of that unit, see how many people would be willing to drink it. No, that didn't happen. Didn't happen very much. I did have 1 or 2 students who did. I didn't encourage it. But the point was they were actually doing something that they had to work, right? Over here on the right, we had a project up the stream with the Bushkill Stream Conservancy that I worked with quite a bit to go in, and there was an existing detention basin there, the kind that gets mowed a lot, that has concrete channels in it. And we went in and retrofitted that to look more like a naturalized basin. And there's real reason scientifically that that's a better way to deal with stormwater, because all those plants and things in there remove some of the volume. Okay. Typically, you run water through these things and it runs out. Everything that comes in goes out. This way, you got water coming in and going out, but also some of it's getting utilized in that system. Some people don't like those. There might be snakes and ticks and other things in there. If it's right next to your house, maybe you're not too big of a fan of it. This is down in Honduras. I will talk about this project in the latter half of this presentation, where we're installing water systems in small villages down there. And then on the right down here is a project right up here on College Hill where after the flooding, which I will also talk about, a few years ago, there was an area of the neighborhood that really got ripped up. And we went in there and working with the city and the Stream Conservancy again, we actually built this constructed wetland. Now this takes time. It took about 3 or 4 years from start to finish to actually have that thing built, but it's up there now. And the neighborhood is really happy with it. The neighbors are real pleased with that way it's come out. Okay, as far as what I do, unlike Drew, I sort of bounce around a lot, and it can create problems when people look at my file and go, so what are you an expert in, Mr. Brandis, Well, I'm not sure, but it all has to do with water, usually water quantity, sometimes quality. Just some of the things. My master's work was on figuring out how to clean things out of aquifers, groundwater, that are similar to oil. So we were trying to take some enhanced oil recovery methods and apply it to these things like trichloroethylene that gets in the ground and you can't get it out. When I did my PhD, I was working on semi-arid systems, I told you, in New Mexico, trying to model how the snowmelt hydrology worked because we were interested in how these radionuclides would transport off the mesa tops. Since I've been here, I've sort of like curiosity-based. Well, I'm here, what's going on around here that my students might be interested in? I've kind of shifted focus more to what the streams around here are doing. Why are some of them more resistant to drought than others? This is a big area that I've been involved in. How does urbanization and land development change the way our streams behave? And of course, that has implications to the kind of the biota that lives there and so on and so forth. So we call it, and particularly base flow, that low flow, that like last week when it was so hot, streams were really low. But there was still flow in most of them, and that's the base flow that I'm talking about here. We looked at some new methods for stream quality assessment using the kind of test kits that normal, ordinary citizens would have. There's lots of these watershed groups now. Some of you may belong to them. They go out and sample. How do we interpret that data in a better way? That's what that was about. And then with the recent flooding on the Delaware, I had a student that looked at how are these big events that we've had going to change how we define where that 100-year floodplain is. And that's a complicated question, and it has tremendous implications. And then the last thing, recently I've always been interested in eagles and why they fly certain ways in the mountains. I got involved in modeling raptor migration as a fluid flow problem. Okay, whatever. It's really neat stuff. We put these trackers on golden eagles. They fly around. We can see where they go. Come back to the models. What is the terrain like there? What was the weather like? And see if we can predict where they go. Why is this important? Well, wind turbines are cropping up all over the place, and people are worried about some of these birds. Most of them, red-tailed hawks, we could probably stand to lose a few thousand of those. They're all over the place, right? Let's get on to the meat of what I'm here to talk about. When you hear about the world water crisis, you're probably thinking about one of two things, or maybe more. One is that we absolutely have this humanitarian crisis going on. It's been going on for a while, still going on. Billions of people don't enjoy the kinds of things that we enjoy. I get up this morning, I take a shower, I don't even think about whether there's going to be water coming down the line. I don't think about, brushing my teeth, when I'm in Honduras, I sure do. But, here, that just doesn't even occur to me. And these are the kinds of things that most of the world has to worry about. And the statistics are staggering and really disturbing. The other thing a lot of people think about is this idea, we might run out of water at some point. Well, I will demonstrate that isn't going to happen. But the problem is the water where we are in enough quantity? I didn't assign any reading. Probably should have pointed this out in advance, but some of you probably get National Geographic. This is the April issue. I'm sure Time, other magazines have done similar things. This just points out just the incredible number of different pieces of this crisis that there are. And I'm not an expert in a whole lot of that stuff. I have a good sense of things, and I have my own perspective on things, and I can definitely talk about what we're doing around here about these issues. This is what I would say is try to find a copy of this, take another look at it. Of course, it's National Geographic. It's pictorial. It's excellent reading, just incredibly good. And it points out that this is an issue that's it's not necessarily about science and technology. It's also about policy and philosophy and spirit and religion, and just about anything you could think of is wrapped up in this sort of water crisis issue. Okay, so what I thought I would do is talk about, on a large scale, the hydrology or the science of the issue of water scarcity. Why do some areas repeatedly have water scarcity, others don't? How would that we touched on this yesterday, and this is something that has got its tentacles in just about any kind of science you can think of, is how's climate change going to affect this? Particularly, we're going to talk about droughts and floods. And then water quality, I'm going to go into a little bit, and more along the lines of what are some of the issues that we think we've licked this problem, at least around here, but the fact is we really haven't yet. I'm going to show you some examples of that. And then hopefully I'll have a lot of time to talk about what we're doing around here to deal with some of these challenges. Okay? A couple pictures here. Some of you may or may not be familiar with this. This is a very famous plot of real data of CO2 in the atmosphere collected on a mountaintop in Hawaii. And it's going up. I think we can all agree on that. And on the right is a picture from Honduras showing a woman and little kids hauling water, which is what a lot of them do, okay, with a lot of their time. Okay. Oh, yeah. Forgot I put this in. This is my wife here and my two boys. My wife is this wonderful sounding board for me. So I told her I had to do this talk, and she said, "You're not going to use equations, are you?" I said, "What do you mean?" "I'm sure I'm going to use a few. We've got to have some." She said, "No, I wouldn't go there." And so I put this up here. Professor Herman paused when he heard that unmistakable thud. Another brain had imploded. So I won't do that today. Ironically enough, my partner over here, Drew, the geologist, did put some up. So what do you know? We got them in here anyway. And the fact is, you don't really need equations for a lot of this stuff that I'm going to talk about. For example, I like to use this picture in my freshman engineering class. Right? I don't think we need to write up the equations for this. Somebody didn't understand the concepts of mass balance or force balance or whatever you want to call it. So we don't always need equations, do we? You have to be careful saying things like that around here. So let's start with this first main heading of hydrology and a subtitle here, Times Are Changing. Okay, I'm going to start with this picture. I assume that probably a lot of you have seen something like this maybe somewhere. I've heard of the water cycle, hydrologic cycle. This particular rendition of it is from the United States Geological Survey. Point is, there's a certain amount of water on Earth. Pretty much a fixed amount and has been for a long, long time, and it will be. Tremendous amount of that is in the ocean, which is not very usable by us unless we apply to it lots of technology. There's a lot of it in ice and snow, and there's a lot of it in the ground. And there's really fairly small amount of it in surface water and an even smaller amount in the atmosphere. But for the most part, this is the part that we're using. We're using some of this, and this feeds this. So they are connected, of course. So we're not going to run out of water. That's not going to be the issue. If distributed evenly, the amount of precipitation available is more than enough for all. And I don't just mean more than enough. It's a huge amount of water. Huge. I'm just talking about the fresh water in this 1%. We could sit here and drink that and go to the bathroom every few minutes, and we'd never get through it all. Trouble is, of course, as you all know, it's not distributed evenly, and we're not distributed evenly, and that's where issues of scarcity come from. And that's the issue we're faced with. So, again, I said we're going to look at the same things, at least for a while, at this big scale. So this is a map of precipitation. This is averages, okay? And I'm going to hit this point more than once. Averages don't really tell the story when you're talking this story. Here we are. Of course, we're lucky because we're in that green blob. And the green, here's millimeters and inches. I still think in inches, probably because of the way I was trained as an engineer. We get 40 couple inches of rain here. And you can see from the colors that lots of places get lots of rain, but there aren't that many people living there. And then lots of other places where lots of people live, there isn't much rain. And interestingly enough, there's hardly any rain in a lot of places you don't think of as dry, is there? Like way up north. We don't see a lot of rain. Point is, you can't just look at the supply side of this equation. There's three things you look at: supply, demand, and then the people. Demand, I mean demand of nature, and that's this next map here. This is a map of the average aridity index. Now, aridity index, what we do is we take the amount, I circled it there, the amount of rainfall, and we divide it by something that we call the potential evapotranspiration. Now, how do we measure that? Well, it's really not that difficult. There's this thing called an evaporation pan, and it's about 4 feet across or in diameter. Probably don't think in tick marks, do you? Feet. And this is about 10 inches. And we have to do a few things to be careful what the wind patterns are and stuff around this. But essentially, think about this. You put this out there, you fill it up with some water, and you monitor it. You can put a scale under it, monitor it by weight. You can put what we call a pressure transducer, and you can automate this so that you get automated data sent back to your computer somewhere. But this is going to evaporate, right, over time. And of course, you probably have right next to that, some kind of rainfall gauge over here, so you know what's coming in, you know what's going out. And so you can actually determine what we call PET is and calculate this thing we call the Aridity Index. So it's supply over demand, and it's more useful because it really tells us how much water gets there and then hangs around for us to use, right? And so now we look at this and we see a different map. In some respects, it's quite similar, but what it shows is that there are lots of places that lots of people live where water scarcity is what you would expect, okay? And you could argue, well, those are kind of risky places to live, and that's the kind of thing hydrologists argue, right? The engineers say, hey, wait a minute, we can fix that, right? We got to work together on this stuff. I circled this. Why did I circle this? I'll tell you why. Drew brought up thresholds yesterday. Remember that? Systems that are near thresholds can switch more rapidly than ones that aren't. That's an area right there. That's sub-Saharan Africa, West Africa. Right now, there is tremendous famine going on there. I mean, go online, look at the pictures. It will blow you away. It will absolutely blow you away. On the other hand, as from a scientist's view, that's a spot with a tremendous gradient of moisture, right? If 1 year for 5 years, remember this is an average, you might have lived there for 10 years and hey, it's always been nice and pretty wet, we've always had enough rain. Something happens in the climate, something shifts. It gets warmer over here, weather patterns change a little bit. All of a sudden you're up there instead of there, right? And so there are places like that. That's a threshold area. There's other places that are very much like that. It's not the only example. Southwest is not so much like that. There are more broad bands of conditions, right? Although with the mountains, that where you are on a mountain slope can really affect what things are like climatically. Okay, so that's what we call Aridity Index, and that's really telling us how much water is there under natural conditions to be utilized. Now, I mentioned this in words. The only way we can live in places like that is through massive waterworks, moving a lot of water around. This is a picture. Does anybody want to guess where that is? It's a Google Earth image. You can all. What? It's Las Vegas. This is the edge of town right now. You can see it ain't going to be the edge of town. In fact, these images are always a few years old, right? It may not be the edge of town anymore. It's a desert. It is a desert out there. It's a place that's going to struggle tremendously with water for its future existence. And it's got problems already. We talked about water level in Lake Mead being way down. The water's more saline than it used to be. It has more salts. That has implications to reuse. If you take water and treat it and put it back and reuse it, the salinity tends to keep going up. So it's not an easy problem to deal with. Okay, what's next? Okay, so I also plotted, gave you the broad statistic that 30% of the population lives in these areas, arid and semi-arid. Just a map of cities of more than 1 million people. This is 06, and I've been pretty bad about labeling on here where I got everything, and so my students would just have a heyday with me because I always get on them about this. And of course, he's back there recording it, so hope I don't get fired. Middle East, American Southwest, there are areas in Australia where we have big cities that there isn't any water. Western India, Pakistan, same issues. Parts of China are like this. So, we've set ourselves up for a lot of conflict and trouble. Global Drought Monitor, you can go online and see, this is at University College London. They have these great maps. This is based, there's different ways to do this calculation. This is based on something called the Palmer Drought Severity Index, and it's a particular way of looking at the rainfall and how much evaporation has occurred and so on. Let's not get into that. But this is showing you currently, well, this is labeled July 2010, drought condition, different parts of the world. Exceptional is over, whoops, sorry, wrong button. Exceptional is that darker red. And then down here it says population in the current view under exceptional drought, 246 million people. And this is the area I was talking about here. Drew, you're going to go up to camp soon, right? Hopefully there'll be water in your lake up there. it's down, right? So we have neat ways of mapping all this stuff now. What was that next slide? Oh, so I mentioned earlier we do a lot of work in Honduras, right? And I will talk more about that. Currently, they're very close to areas that are very dry. We work right about near where that X is there. And we're okay right now, but a lot of places around us are struggling with drought conditions right now. And this, it's not that drought is unusual, is what I'm going to point out. There's always drought somewhere, and we're always struggling with this. Now, at the other end of the spectrum, we can look at flooding, and if you want to know about what's going on in the world in flooding, you don't go to University College London, you go to Dartmouth. I don't know why, but that's where you go. They have this really cool global flood mapping that they do. This is just for, last week I pulled this one up. You may have seen in the news a tremendous flooding going on in Monterey and Mexico and places like that. And I think the numbers just mean the incidents in this given year. I'm not exactly sure. And this is a map of reported floods throughout the first half of 2010, and things start lighting up a lot more, right? Point is, floods and droughts are sort of, in a sense, normal. What we have up here, though, is interesting, and it's going to lead us into this issue of change. According to them, they've been tracking this now since the mid-'80s, and you always wonder if somehow the methods or the data has gotten better, but they show both sort of moderate floods and bigger floods, and I forget exactly what M4 and 6 means in this context. Both of them are going up. The incidence of these, the number of occurrences of these types of flood are going up, which is really interesting and probably related to this. Okay? Now, you can talk about flood damages going up. That's a little bit different, right? Flood damages relate to how many people, how much infrastructure are there when that flood comes through. Actual incidences of floods probably related to something going on in the, quote, the natural world, the climate. So I put this up earlier, right? This is that plot, very famous plot back to the late 50s of actual measurements of CO2 in the atmosphere, and you can see that there's this up and down, and that signal relates to growth of plants. Most of our land is in the northern hemisphere. The plants are growing, taking up CO2. In the winter, CO2 goes up. But the trend is up, right? And looking at actual data now, I'm not going to get into modeling because I'm not a climate change expert, atmospheric modeler. This is just data we're looking at. Same time period I shaded over there, global average temperatures. And this includes both, I believe, both sea surface temperatures and ground-based temperatures. The people who do this work always talk in terms of anomalies, okay? The difference from the mean, okay? So 0 is the mean, difference from the mean, so it's positive. That means it's warmer than average. It's going up, right? It's going up. This curve kind of looks a bit like that curve. They're probably interrelated. You ever hear of Occam's razor? The simplest explanation is probably the right one. It isn't always, but it's probably, and I suspect those are certainly connected. We think they are. That's pretty well established. Question is, how does this affect water crisis and what's going on with the water? And that's a really interesting question. There are certain things that are unequivocal, and that is the fact that all that water that we had stored in ice and snow, feeding those meltwater streams that Drew showed us yesterday, if that's disappearing long term, and we know a lot of places they are disappearing, that has huge implications to people and their ability to get water. Just some examples. So the Himalayas, these are some big river systems in the Himalayas, and how many people live there and depend on that water, right? The Indus, 180 million, Ganges, 400 million, Brahmaputra, the Yangtze, going over eastward into China. In the Andes, there are cities, Ecuador, Peru, Bolivia, that's where the water comes from. And of course, in our own country, in the southwest, the Colorado River and other rivers like the Platte, if all that snow and all that ice disappears, this isn't going to happen overnight by any means. And you know about the Intergovernmental Panel for Climate Change. A lot of scientists working together under auspices of UN. They come out with reports in 2007. They got in a report that I I think it was the Himalayan glaciers were going to melt by 2035. Okay, and they caught a lot of flack for that because that's crazy. The real number is 2350. Okay, now they claim it's a typo. I've done things pretty bad like that. I could see where that could be a typo, but of course, so the point is it's not going to happen by 2035, but hopefully we're all going to be around and our children's children's children will be around when it maybe is going to happen. So looking at huge changes down the line. That's how many? 300 plus years away. Engineers don't think a lot about that. Geologists don't even either because they're thinking in millions and hundreds of thousands. But we got to think in those time scales too. Okay, that's going to happen, but I wouldn't say it's a crisis right now. So the question is more, what's the shorter term impacts on water scarcity? Not just scarcity because floods is a big issue too in places like this. Where I live, or here in Pennsylvania, I don't know, I'm sure there's a wide distribution of places that you all come from and things that you touch every day. But the general thought from many scientists, and it certainly makes sense from the perspective of physics, is that there's going to be more moisture in the atmosphere. It's a warmer atmosphere. It's going to evaporate more and it's going to rain more in other places, right? It's going to be a more active system. And around places like this, we're going to feel this probably. And it's going to be felt in extremes. That's the thought. These effects will be felt locally in extremes. Wet areas will tend to get wetter because it's warmer, more moisture, more rain, more intense storms. Dry areas get drier, more drought. And this is becoming, pretty much everybody of repute that has studied this. I put one citation here from Nature a few years ago that this is based on, but it's not nearly the only study. There's lots of studies, and this is what we think the direction is. Now, I put in yellow here, though, and this has come up a lot in my own work. Natural variability in weather coupled with large-scale anthropogenic effects, things like the land is changing because we use it differently, population's moving, water projects are moving water around. It's hard to find these effects against all that big noise. It's hard to see, perhaps, these effects of climate change to be able to pin things down and understand, oh, that's happening because of climate change. That's a difficult thing to do. I will give you a simple example. One of the things I've been interested in is, since I came to the Lehigh Valley, how have stream flows changed due to suburbanization of the Lehigh Valley over the past 50 years? Now, the Lehigh Valley basically goes from Phillipsburg, Easton area over here to Allentown. This is, again, an aerial view. All the stuff that looks gray is lots of houses. And so a lot of this has cropped up within not just the last 50 years, but say the last 30 years, right? And the real nice situation here for a hydrologist is that we've got pretty good data sets right around here. This is the Lehigh Valley Airport. Almost any airport that's of any size has a weather station because, of course, you're concerned about flights coming in and out. Got good data on weather going back 50 years. The other dots are where we have gauges on the streams, and USGS is the people who do those, and those also go back 50 or more years. There's two here on the Lehigh, down in Easton at Glendon, up near that other school, starts with the L up there. That's right there. And those other three dots are smaller watersheds. Drew had a picture of a watershed in the land area that drains into a certain stream or river. So these other three are on local watersheds. And I thought, wow, this is great. I'm going to get a few students. We'll crank through some of this data and we'll see what's happening. We'll look at trends and look at the precipitation and so on and so forth. Well, here's the problem. Weather is highly variable, not just a little bit, highly variable. When somebody says, oh, the average temperature for today is 86, yeah, well, so what? What's the range of variation? How often is it 96 instead of 86? So weather variability, huge. Dams, well, I found out real quick that gauge is right below the chain dam on the Lehigh River. Basically can't use it. The water flow past that gauge is highly influenced by the fact that there's a big dam there. There's also other dams farther upstream, so it kind of affects how we look at this other one's data because this one was, I forget when F.E. Walter was built, but it's a flood control dam, so the flooding has changed significantly. These other ones, we didn't have those kinds of problems, but what I did find is that there's a lot of, people live there. Equate that with a lot of artificial movement of water, okay? Piping systems leaking water, piping systems moving water from one watershed to another, big Nestle plant here pumping water out, putting it in bottles like this one, moving water around, and that's hard for me to account for if I'm looking at rainfall and evaporation and stream flow. So this became much more complicated than I thought, and which, in our practical little academic world, much more difficult to publish than I thought. But it was very instructive for me and for my students, and so we got a lot out of it. I will show you one example of the actual data. This is the little Lehigh Creek near Allentown. It's west of Allentown, just on the other side of Allentown. And it's remarkable. This is a remarkable data set. This is the peak stream flow every year. Now, this is in cubic feet per second. It's a measure of volume per time. So it's the peak of when that flood wave came through, what was the maximum volume of water going past there in a second, right? That's the number that's plotted. And for every year, we figure out what was the peak event, right? Well, things look pretty nice and sort of things are going along at some sort of normal way from the beginning to around 1970. And then all of a sudden, what we see is, number one, the mean seems to have jumped up by at least a factor of 2. And the variability's gone all to hell, right? Well, this is interesting from a water manager's point of view because everything we do is predicated on sort of these things like what's the 25-year storm, what's the 100-year storm, right? Well, if all of a sudden, what's the 100-year flood? If I'm near a floodplain, any of you live on a river, near a river, okay, you may care, where really is that floodplain? Because, of course, you got to buy insurance perhaps, and you might get flooded out more often than not. But we're in charge of predicting where that line is. If all of a sudden the 100-year flood went, from somewhere here to somewhere there, that has huge implications to people in the world and politicians. Oh, crap, I got to tell all those people down there that can't live there anymore, So really interesting data set, and the only explanation is the climate around here. There was a lot of drought right in here. And then it got wet, and it stayed wet for a while. And on top of that, we had a lot of people moving in, building going on, land development. So really kind of interesting story. Okay, this is, again, real data. I'm not going to show you any model predictions of anything. What's happening to temperature? Well, red is going up, blue is going down. It's either in a few places not changing or everywhere else it's going up, okay? It's going up, and where's it going up the most? Down there. Uh-oh, trouble, right? It's a dry area to begin with. On the right, changes in precipitation, right? It's almost all green and blue. Now, some places in the west, I don't like the color scheme so much, it's precipitation rates are going down, which is sort of the trend that you, would expect to see. So real data, things seem to be changing in the ways that we would expect them to with climate change. Of course, variability. I'm doing this gardening project, and I'll show you that too. It's up here, up by Metzger Field. I don't know if any of you drove up there. You see this big garden, kind of rough looking in spots, a little bit weedy now and then. Last year, we put in this water system. We never hardly used the thing last year because it just rained and rained and rained. And it was cool and damp last year. And that way true for a lot of the country. This summer, different. We've already run out of water up there once. And that was last week. Last Tuesday. Boy, it was out of scorcher. Time here was 2:45 p.m. And you see, what kind of conditions we're dealing with. That's temperatures. That's from the Weather Channel. The thing down here is a plot from the United States Geological Survey. It's, again, a color-coded map. Every one of those dots is where we have a stream gauge on a creek, on a river, on a reservoir, surface water. Anything black or blue is experiencing, near flood, close to flood conditions, right? Very high for this time of year, for that day of the year, a lot of flow, right? Greens, sort of average conditions. Reds, very low, okay? And you can see what conditions were like as of last week. Now, that got moderated a little bit. We had quite a bit of rain here, actually, on Sunday morning, was it? But the streams went down really quickly, and the reason they did that is because it was so dry. A lot of that water just got sucked up by the ground. And in the summer, when the water gets sucked up by the ground, it's going to go to the plants. It's not going to go much back to the stream. The plants are going to use a lot of that water. So tremendous, a lot of drought through this region. A lot of things happening in the upper Mississippi. It seems to be wet there a lot these days. Okay, now, some parts of the world, a few, are really taking this issue of climate change has changed our water system very seriously. In southeast Australia, there's an area called the Murray-Darling Basin. And it's a large, mostly semi-arid basin, lots of water projects, aqueducts, dams, so it's heavily controlled. There's hydropower there. This is the average long-term inflows into that system, monthly inflows. What's a GL? Billion liters, maybe? I'm not sure. Point, though, is this is the general trend. Now, why does it go up in July, August, and September? It's their winter, right? It's the austral winter. Okay, so that's, well, the winter's here. That's the snow melt season, right? So that's the inflow of all the snow. That's just the average. Then it drops, and it's an annual cycle. That's an average. Now, the last number of years, and this has been going on for about 10 years, and it's moderated a little bit this past year, but it's enough that the people have decided we can't wait around and hope that it changes. We've got to make changes in the way we use and manage water. These are the inflows for these other years here. The red line, so it's incomplete, 2009-10. Yellow is the year before. This is the year before. Black is 06-07. I mean, those people are looking at serious, serious drought. And looking at graphs is one thing. Pictures, talking to farmers is another. I mean, a lot of people, sheep farmers in that area have given up. But what they had to do is they've instituted water rationing, and it's based really on what the immediate security needs of the country are. So drinking water is number one, always takes precedence. But so irrigation's below that. There's been cuts in those rations. Okay, we haven't done anything yet like that in this country. Cuts to rations to farmers. They've done that. What have the farmers done? Well, if they're still farming, they have changed the way they irrigate big time. They've gone to more expensive, more technically involved systems of drip irrigation, actually monitoring in real time what their land is, how dry it is. But it can be done. And restrictions on personal use. Can't water your lawn, can't fill your swimming pool, lots of things like that come into play in the Murray-Darling. And that has happened just in the last few years. Now, that's in the Murray-Darling. Well, what about here? More flooding is what we think we might see, right? Do we care? Well, we sure do around here, don't we? Since we've invested a lot of money down there at the bottom of the hill, right? This picture's from 2005. That's the Visual Arts Building. Now we are going to have a nice film and media studies center down there too. I talked to my buddy Andy, who's the department head. He said, I know I can't put anything valuable on the first floor. I know. This is the Chamois Shine car wash. I don't know if you've seen that. It's just a little bit down of here, okay, with people canoeing through there. You don't see that every day. This picture, this is 2005. I put up, this is 3 different years I put up here. 2005, 2006, 2004. That hasn't happened very often around here. That's the...
Yeah, did it exceed the famous Eastern flood of 2000?
No. None of these are really anywhere close to that. These are big floods. In fact, 2 of them are about 100-year floods. One of them is maybe a 50-year. Consecutively, that's what's most interesting, right? Certainly got a lot of people's attention. Yeah?
When you say 100-year floods, what do you refer to?
Yeah, that's a whole talk. In fact, I thought about giving that talk instead, but I thought this would appeal to more people. It relates to, it's just horrible terminology. It's insurance terminology. What a 100-year flood means is that there's a 1% chance of it happening this year. Okay, so if you take 1 over 1%, you get 100. And so people think, oh, well, if there's a 1% chance of it happening this year, that means it probably happens about once every 100 years. Totally wrong. Totally wrong. That's not at all true. Random systems don't space themselves evenly, ever. Okay, so just really bad terminology, but that's what we're working with. Yeah, and thank you. If I probably say things up here, you have no idea what I'm talking about. Please stop me, because there's the rest of you are all you're probably in the same boat. Oh, did I get everything I wanted to say? Yeah, so just where is this 100-year floodplain? Well, if we can figure out what the 100-year flood is, we can maybe map this floodplain, right? You know, the whole concept of the 100-year floodplain is a weird one, because there's nothing particularly different about the 100-year than the 200-year than the 75-year. We just happen to pick that one, okay? And if there's a 100-year flood, there is a 200-year flood, which is bigger than the 100-year flood, right? There's nothing magical about that, unfortunately. So this is the actual data. So somebody's question, this is the Hurricane Diane storm in 1955. That was a huge one, and how are we doing on time? When am I stopping? 10. All right, I have a 9-minute movie I'm going to show you. I should probably pick up the pace a little bit. But there's the data. These are the 3 big floods of 4, 5, and 6. It's definitely highly unusual. They're 3 of the biggest 6 on the map right here since 1904. Now, as it turns out, a little bit before this, there were 3 big floods before the gauge was put in. People marked, particularly in Trenton, there were marks 3 consecutive years, really big.
How can you prevent that flooding downtown?
Well, that's a good question. See this thing I put up here? These are signs you see all along the river. Governor, stop the Delaware River flooding. You can't prevent it. You can learn to live with it better. You can flood proof, okay? You can flood proof your home. You know, in some places, they actually have moved neighborhoods. Bought people out and said, this is not a good place to build. Let's make it into open space. The problem is, let's watch the movie, because I think it'll help directly with that question. Just one more point before I go to that. Drew and I have gotten involved with a local NGO that's interested in this very issue, and this issue of flooding, and how can we better help people understand the real risks and what's involved, and the fact that, you know, there are limits to the amount of control. A lot of people, Tox Island came up yesterday, right? You started hearing a little bit of hue and cry for maybe we should have put Tox Island in, right? Thing is, there's flood control reservoirs on the Lehigh, right? The Lehigh flooded. A lot of times the same as this one, maybe not as much, but it doesn't prevent floods. And sometimes what it does is it gives people a false sense of security, and people start moving into places where they shouldn't. So preventing is probably not what we can do.
What's
okay.
an NGO?
Oh, non-government organizations, non-profit. So this movie that I'm going to it's a 9-minute clip. It was put together by a guy who's working with them. He's a flood safety guy, but it's about. I tried to embed it every time I try to embed something in the PowerPoint, it doesn't work. So let's look at it this way. Can you see that? Yeah. I might have to crank up the volume here.
Deep forests and magical streams.
High as I can put it.
The utility of these waterways helped the state become a manufacturing powerhouse, churning out the coal and steel that fueled the engines of America's industrial age. But with so many cities built right down on the water's edge, it's no wonder that this area has suffered from so many devastating floods. And over time, Pennsylvania has tallied the greatest amount of flood damages for any non-coastal state. The first big flood event, and arguably one of the worst natural disasters in all American history, was the Great Johnstown Flood of 1889. Johnstown was a bustling steel town, and like so many others in that industrial era, its mills were built right on the river to transport materials and get rid of waste. The city already had a major flood problem since it's situated at the bottom of a narrow canyon. But the mill owners and townspeople had become increasingly vulnerable to a poorly maintained earthen dam just 14 miles upstream from the city. And then it began to rain. hard.
It was generally assumed that that dam was going to break someday. But the tragedy was no one knew what the consequence would be if it did. 2,209 men, women, and children had perished in the flood. The biggest single-day civilian loss of life in American history until 9/11.
A closer look at the topography around Pennsylvania shows elements that contribute to the chances for heavy rainfall and flooding. The first is the state's vulnerability to large air masses moving in from the Great Lakes or the Atlantic coast, which can deliver hurricanes inland. Second, on its western flank, Pennsylvania is subject to storms moving up the Ohio River Valley and being stalled by the Appalachian Plateau. And lastly, it sits at an overall latitude where large storm systems are likely to develop and stall. And this is what happened in 1936, when a series of late winter storms brought wide-scale disaster throughout the entire region, and practically all the major urban centers in Pennsylvania were hit hard.
America is suffering its major flood disaster.
Johnstown was hit again, devastating the downtown and killing a dozen people. Pittsburgh had 21 feet of water in the business district, and fires threatened major portions of the city. 45 people died there. Harrisburg was flooded and major transportation lines ground to a halt. And in Easton, rivers of ice water flowed past and through houses built right by the Delaware River. In 1955, Hurricanes Connie and Diane hit the Northeast, just 5 days apart. This brought up to 17 inches of rain and major flooding in the Delaware River Basin. 99 people died in that valley alone, with many more deaths throughout the area. In Stroudsburg, Broadhead Creek cut the city in two, collapsing dozens of bridges and many small dams. And in Easton, the great span that had survived the big floods of 1903, 36, and 42 was ruptured by the remains of an old covered bridge that came crashing down the river in the darkness of night. And then in 1972, Hurricane Agnes made its way up the East Coast and brought torrential rains to the Pennsylvania interior. Wilkes-Barre was hit particularly hard, and downstream on the Susquehanna, Harrisburg, and even the governor's mansion were inundated. This event killed 48 people, destroyed 68,000 homes and 3,000 businesses, and left 220,000 Pennsylvanians homeless. This recent history firmly establishes Pennsylvania's flood vulnerability, but it also raises questions about how so many areas that have been protected might still be at great risk. Back in Johnstown, this issue was addressed by Mother Nature with a violent thunderstorm in the summer of 1977 that brought floodwaters raging through Johnstown yet again. In all, 78 people died in the Johnstown area, and the city saw major devastation for the third time in 88 years. What's important to note here is that much of Pennsylvania and the nation has been built to withstand the so-called 100-year flood. But we're seeing signs that some areas are likely to experience damaging floods on a much more frequent basis. And climate scientists are telling us that large, damaging floods may be occurring more frequently and with greater intensity. In Easton, for example, in 2004, Hurricane Ivan brought another 100-year flood disaster to a city already hit by 5 major floods in the previous 100-year period. But just 6 months later, a flood that large came again in 2005, and then astoundingly a third time in June of 2006. This made for 3 100-year floods in less than a 2-year period, and obviously signals that more must be done to prepare Easton and the rest of Pennsylvania for floods to come. With recent flood disasters in New Orleans and the Midwest, America appears to be waking up to the fact that assumptions about man-made protection from floods must always be questioned. And all throughout the nation, cities and citizens must do more to prevent and prepare for damaging floods. In Austin, Texas, this building was severely damaged by a previous flood, but the new owner made several improvements to help floodproof the structure. The first floor was wrapped with a waterproof membrane, and the entryway and electrical systems were elevated. A few years later, when another flood devastated businesses on either side, this building stayed dry. In Las Vegas, where flash floods threaten, grade school classrooms study how floods develop and what to do to avoid being caught by one. And in Tulsa, Oklahoma, whole neighborhoods that saw repeat flood events have been removed from floodplains to provide welcome open space and parklands. And so, Pennsylvania, with many large cities and hundreds of communities at risk from damaging floods, has a great challenge before it. For along with our success at preventing the more frequent, smaller floods, one simple truth remains. Any town that has had a large, damaging flood is likely to have one again. Today, the mills are largely gone, and the rivers are a great source of recreation for all ages. But there are still many at risk from the river's power, and there's more work ahead to create communities living in true harmony with nature.
Okay, so remember, this is produced for the purpose of trying to educate. Let me get back to the slide. Educate the local community more about what the risks really are and what can be done about it. We probably need to keep moving, but is there any real burning question that we want to talk about the move from the movie? Okay, good. Okay, let's move to water use. And the main point I want to make here is that when we talk about water, all of the things, the big challenges that we face globally, turns out they're all interconnected. We can't really solve one without thinking about the others. So in the U.S., and I'll show you a graphic for global as well, most of the water we use goes to agriculture and most of that to irrigation. And close to that is power generation, believe it or not. Okay, power generation, most of these systems run steam turbines, right? That's how we generate electrical power. Lose a lot of water due to evaporation that we don't recover. Public water systems, pretty big user in other industries, 5%. If you look at the top water using states, California, Texas, Florida, not too surprising. Idaho. Why is that? Irrigation. Huge irrigation going on up there, as well as power. Yeah. And dams are considered consumptive. Hydropower is considered consumptive because if you need a certain amount of water to run your turbines, that water can't be allocated to somebody else, right? So even though the water goes through it, it's still allocated.
Yeah, that power generation number jumped out at me. So that includes hydro generation?
It does.
Which doesn't remove water from the system.
You're right. So that may be a bit deceiving, right? Good point. Worldwide, much more towards irrigation. Okay, and why irrigation? Well, look at these pictures. Okay. Again, I'm not an expert on agriculture, but these two pictures, believe it or not, in Arizona, right? Okay, I don't think that particular farmer is too worried about conserving water. He's got a certain allocation and he's using it, right? In the Murray-Darling, the allocations went down, and my guess is a lot of farmers will figure out another way. Furrow method he has shown here, flooding, this is wheat, they'll flood the entire field with water. We see a lot of this in the east. These pivot systems, big, they go slowly around the field, they're high pressure. They're actually much better in terms of water use than either of these, but still a lot of wasted water. The best system that we know about is, in this picture, is I believe from India maybe, it's from the third world, I know that, is a drip system. These are the little dripper here. And then you can actually combine that with actual real-time soil moisture monitoring and really do a really excellent job of reducing water use tremendously. It's possible. It's more complicated. New equipment's involved, so there'd have to be some capital investment for these farmers to do this. But we can do that. Unfortunately, the history is that a lot of groundwater has been used for irrigation. And when you use groundwater, and this is something we didn't understand well until maybe the last few decades, or 50 years maybe, or we maybe understood and it didn't matter, is that you got to be careful how much you take out of the ground, because if you take too much, you're basically mining it. It's essentially fossil water because it got there over very, very long time scales. It's not quite fossil time scales, but that's the term people like to use. Two examples. This is in the Santa Clara Valley. This is now Silicon Valley. Used to be all orchards. A lot of beautiful orchard land. This is a plot of the depth of water in I think it's just one particular well down there around San Jose. Water going from near ground surface. In fact, this area had a lot of, what's the term? It's escaped me. What are the wells that just naturally flow? Artesian, yeah. This area had a lot of artesian wells. It started up near zero, down to 240 feet in the 60s. What saved them? Well, water switched to surface systems from other places that were brought in. And as you know, there are more profitable things to do in San Jose than grow oranges these days, right? This is the Ogallala Aquifer, which is western Great Plains. That's a semi-arid area, western Great Plains. A lot of water use from that aquifer. It isn't going to get back there anytime soon. So these are reductions in water levels since 1950, declined more than 150 feet, 50 to 150 feet. So a lot of places have used that groundwater. There's a lot of it down there. Unfortunately, once you use it in a lot of places, it's not going to come back very quickly, at least not on the time scales we're interested in. Virtual water. This is a really interesting concept and one that I wasn't aware of or really had thought very deeply about until recently. Virtual water is, so it's sort of terminology, the amount of water that is needed for production of food or other products. And we think about what we eat not in terms of water usually, right? But as it turns out, probably the worst thing you can do is eat a steak every day in terms of water, because the amount of water, if you go trace it back through the life cycle that goes into production of beef, is huge. A lot of that through irrigation. So the way we eat affects water. Where that water, how much water, where it's coming from. Some things, it hasn't stopped me from having a steak now and then. But I try to eat more chicken and fish and other things partly because of this. Kind of healthier too. So this is really an interesting concept. People have mapped, based on commodity, grain, beef and stuff, this sort of water cycle around the world. And this comes, I believe this is from National Geographic too, I think. And we're primarily an exporter. We use a lot of our own products, but we're primarily an exporter of this sort of agricultural virtual water. Amazingly, Africa is an exporter of virtual water. Can you believe that? Some places like Japan, Italy, import huge amounts of this virtual water through food, through consumption. So it's a whole new idea that a lot of us wouldn't think in these terms. It's quite interesting the way these things are interconnected. Okay, this energy production, as I said, this is thermoelectric, a lot of this, right? And again, hydro is sort of a unique one. But fossil fuel, nuclear, those are thermoelectric, steam generation, or steam turbines, really high water use, okay? Very high. A lot of that water evaporates, it's lost. On the other hand, photovoltaics, panels on your roof, wind, they don't use much water. I tried to find numbers. What I found is everybody has different numbers. So I said, well, let's just go with, the sort of qualitative scale. And then biofuels, one of the problems with biofuels, you may have read some of this, is a controversy about ethanol and its sort of energy content is one issue, but it's a huge user of water because of the corn that has to be grown to produce it. So, boy, it's interesting how now I've talked about food and energy all of a sudden, isn't it? In this, yeah.
Question. Why don't we require the power utilities to condense and reuse that water? It would be less energy to reheat it.
Yeah, operating costs, I think. A lot of it is evaporated. They have evaporative cooling towers, and they have to return it back to
Tanks, and it's already warm.
to the river. A lot of it goes back to the river.
Back to the river, yeah. Grows the fish bigger, though.
Any sort of a boiler operation, over the course of the use of the steam, you continue to concentrate salts in the circulating loops of the boilers.
Yeah.
So there's a certain fraction that has to be taken out periodically, and that's referred to as boiler blowdown.
Yeah.
So you have to remove so much just to maintain the system so that it doesn't foul. So that's one of the major reasons why you can't continue to reuse it.
I just wanted to bring this up. In our area, all of a sudden we're facing this issue nobody ever heard of a few years ago, the Marcellus shale gas. Large area of Pennsylvania, New York, Ohio, West Virginia. We've known it's down there for a long time, but now we have the technology to get at it with the horizontal wells, and there's this, what's called fracking. They go in there under high pressure and inject chemicals into the formation to create a lot of microfractures so we can get the gas out. This uses a lot of water from whatever the local source is. It produces a lot of wastewater. You get some of these fracking fluids have chemical, now I'm talking water quality all of a sudden, have chemicals. So, connected with energy, now we're dealing with water again. There's thousands of these wells just in Pennsylvania alone. I had a student map some of this. Hundreds of those are near our high quality streams and our EV streams, which is exceptional value. So it's a great economic boom for a lot of areas, lots of potential for farmers and people, ordinary people, to make a little money on the side to keep their operation going. There's also a lot of potential for water resource damage. A few realistic solutions here. Well, I've already mentioned irrigation. We know we can do better. It's going to there'll be some pain involved, cost, but that can be done. This is tied to energy now. I'm not a believer that we're there yet for the alternatives. We don't have that much technology and that much capacity to produce the kind of energy we use with alternatives yet, but hopefully we'll get there. Reclaimed water. Some places are already doing this, treating wastewater, blending it back into the potable water supply, or using it for irrigation, or actually just recharging the ground with it. And we're going to have to do more of this, particularly if the climate, these risky areas, just through their natural conditions, if climate shifts to drier conditions, you're going to see more of this. Thankfully, for people like us who've got means, we can do that. People always ask me about, well, what about desalination? Guess what? This is connected to energy. Yeah, we can do it. And people with the means, the Middle East, huge desalination plants. And they even do some of it by distillation, which takes tremendous amounts of energy. But they've got it right now, and so it's okay. We're doing it in Florida. This is Tampa. This is the biggest, as far as I'm aware, the biggest desal plant in our country. Notice where it's located. It's co-located with that fossil fuel, coal-fired power plant. Why? Because it uses so much energy. And in fact, they are using cooling water from there to feed this plant. So there are reasons to co-locate these things, but they will use huge amounts of energy. So we can do it if we have to. It's got its downsides. It's not going to help a lot of the world deal with their problems. And it's expensive, and of course, operating costs are going to be directly tied to energy costs. Water quality, I don't have too much time to spend on this, but the point I want to make is that there are new challenges that we're not done yet. We started out here. Anybody hear of John Snow? This is an epidemiologist working in London, looking at the incidence of cholera. At the time, people thought cholera came from bad air somehow. That was the leading theory. And Snow made this plot, very famous plot. Each one of these little dark bars is incident, or maybe 10 incidences of cholera, I can't remember, and mapped where the pumps are. And of course, everybody, there was these, manual pumps. You went and got your water. This is Broad Street in London. That's a pump there. These other ones circled in blue are also pumps. And what he did in what we like to call, the engineers, the first act of environmental engineering of all time, he removed the handle of that pump, and the problem went away in that area. And so he was a very clever guy looking at patterns and figuring out what was going on. He's an epidemiologist, not an engineer. But so we know that water and disease are linked, and that statistic I had earlier, 9,000 children a day. I mean, most of that's waterborne disease. So we've come a long way since then. Go down, what is that, 125 years to the Clean Water Act. This was the goal, the national goal, that the discharge of pollutants into the navigable waters will be eliminated by 1985. And we haven't done that. I think the people who wrote this maybe didn't really understand what they were up against.
They understood what they meant by the word goal.
Yeah, well, that's right. Very good point. That's right. That's the goal. We don't know how far we're going to get, but that's the goal. Some of you probably saw, and I'm going to just point out a few examples from this series that ran in New York Times over the last year, Toxic Waters. Really nice series. And they highlighted a few of the issues, and that's what I'm going to do. We have a system of aging sewers, 50, 100-year-old sewers, most of our cities, that weren't intended to last forever. They all leak. Furthermore, a lot of the systems are what we call combined sewers. So, for example, most of the big cities on the East Coast are like this. You have a sewer system, and then the storm drains, like when it rains, it goes down those drains, are connected into the sewer system, right? So as long as it's not raining hard, the sewers can handle that flow. It's not a big deal. But what happens when we had 5 inches the other day at the airport. Incredible. And that was over like 3 hours. Well, all that water is going to, the capacity of that sewer to carry that water, it's not going to work. And so these things have these sort of like a flapper valve that opens up when there's enough pressure and releases all that water out into the harbor. Okay? Untreated water, sewage mixed with the runoff from the streets. That happens all the time. So wet water condition. Anytime we had a big storm, if you're out sailing in the harbor, I don't have a sailboat, but if I did, I wouldn't jump off the boat. Not in wet weather conditions. So we have that issue, and that's a lot of money to fix that. Recently, there's been, the courts have challenged this idea that that this Clean Water Act applies only to navigable water. Right? Well, it's always had been the case that anything connected to navigable water, it could be a very small stream or a wetland, was part of the navigable water. Now, apparently there's been a few cases where that's been thrown out. These ducks are at Avondale Creek in Alabama. Court ruled the waterway was exempt from the Clean Water Act. Okay? Now, we're going backwards here, right? I mean, I've got 2 little boys. I don't want them playing in that creek anymore. So actually, enforcement cases are down in recent years. Now, we can argue philosophy about what's the right way to have clean streams and whether it's a command and control kind of approach or not. But I kind of favor strong regulations on things like clean water. We got a lot of low levels of pesticides in our groundwater. Atrazine. Anybody ever heard of atrazine? It's used herbicide commonly used on lawns. Certainly in the corn belt, lots of this is used. So there's lots of atrazine in water at very low concentrations. It's controversial whether or not that's a problem. I don't think we really know. I like the precautionary principle. I would rather not have it in my water that I'm drinking because I don't know what might happen to me, right? So that's still there. Here's a really great picture. This is from National Geographic. This is a rendition of a fish farm, okay? These are pharmaceutical chemicals, personal care product type chemicals found in a particular waterway near Chicago. We all use pharmaceuticals every day. we'll throw some out, maybe flush them down the toilet. We excrete them. I mean, we can't stop excreting them, right? But they are in our water. There was an interesting study a couple years ago of pharmaceuticals in drinking water, okay? Tested positive, even Little Easton's on the map. Philadelphia had 56 different drugs found in its water. Now, these are very, very low concentrations, right? Parts per trillion or something. But, you know, if you got this, plus this, plus this, plus this, and I drink it all my life, well, I don't know about that, right? Now you know why some people say, well, I'd rather take my chances with this, right?
Probably has some in it.
Where does that come from, right? That might come out of a tap in Philadelphia. Of course, hopefully they're Allentown. All right. Yeah, I already showed that. Interesting, huh?
We have good water in Seattle.
Seattle. That's the place to go. And it's pretty wet there, right? Okay. Well, I've got 15 minutes left. I would hope I would get through, maybe I have too many slides. I always do that, right? Tackling a global problem with local solutions. Now, I understood that locally we don't face the kind of problems that some places face. And so what we do here to conserve water isn't going to help the people in sub-Saharan Africa too much, right? I understand that, but I think we have to lead by example. Okay, where do I start? Well, in 2007, this group came out. Nobody had ever heard of them. They rated colleges on sustainability. And they had 8 or 10 categories. What do we invest our endowment in? You know, what's the administration like? What are the students doing? Energy, what have we done on campus for alternative? Oh, they had 8 or 10 categories. We got a D+. Now, that other school up the road got a D+ too. So, not that we ever want to be on the same level as them.
Tied.
But I brought this to the attention of the Trustee Committee on Grounds and Buildings that at the time I happened to be representing the faculty on. And I can't claim to have been the one who instigated all the change that's happened around here, but it got people's attention. I mean, because it's bad publicity, and perception is reality in the world we live in. And furthermore, there were a lot of things we could do that we weren't doing. So the following year, our president, who talked yesterday, signed a climate commitment that many university presidents have signed. And it actually commits us to quite a few really concrete steps to try to reduce. It's related to climate change and reducing carbon emissions mostly. But it says we exercise leadership in communities, provide students with knowledge and skills needed to address the critical systemic challenges faced by the world in this new century. And I like that because, as I've showed, well, this stuff is interconnected. You aren't going to solve one problem and then, okay, we licked that, let's do the next. Anybody know what that graph is over there? That's the Dow Jones Industrial Averages. The red line is January of 2008. So we've been working with, a shorthand, especially the year or two just following that. Nonetheless, we've done some pretty neat things. Campus Master Plan came out last year. It says some very specific things. The college will start to look inward to supply some of its water needs by collecting rainwater for reuse in buildings and irrigation. Lafayette will also reduce potable water demand through conservation, reuse, and recycling. That's the map of what campus may look like down the line. We also came out with an energy policy that talked about water. So I don't know if they anticipated this connection between water and energy, but it does cover some things. Use of irrigation water shall be minimized through rainfall monitoring. Now, I happened to take that picture at the heat of the heat last week, so we still have a way to go. This is a sprinkler head that rotates around and it waters the sidewalk over there, and it goes through this, then it waters the pavement over there. So it's not ideal by any means. My students have estimated that a 1-inch rainfall on our campus generates 1 million gallons of runoff. By looking at the different types of lands and how much area in each one and how much runoff we expect, that's a lot of water that we could be using with just 1-inch collection. So other things, they talked about low water use, flush valves, waterless urinals, and flow restrictors on faucets and so forth should be used in restrooms. Now, I don't know how much retrofitting we're going to do, but certainly new buildings will be using that. The students worked on a project. If we retrofitted 3 dorms, what would we save? 50,000 gallons a week is what they came up with. In terms of dollars, we pay for our water, right? 175 a week. Now, that's not going to pay for itself real quickly, right? But still. And again, like I said, these are all local. When you talk about water scarcity, the fact that we're saving 50,000 gallons probably doesn't really mean that much here in Easton most of the time. But you get into drought conditions, which we do get into, and that might be a nice thing to be able to say. More incremental progress. We have these filtered, these stations for filling up your bottles, like your stainless bottle, you refill that with filtered water from the tap. I'm really setting a bad example here today. I got this yesterday out on the table. I came to Drew's talk. We have a compact fluorescent replacement program, Energy is Water. We did a green roof installation on the engineering building to see what that would cost. It was sort of a trial run. What's it going to cost? How much engineering is involved? Could we upscale this with reasonable cost to other parts of campus? And I've actually instrumented a model right next to that where we measure how much water we trap by that. And the students, it's about 1 inch. You can get about the first inch with a system like this. But you could then, it's got these particular types of plants, sedums, that are adapted. They can handle drought conditions. It can be really dry and they'll still be alive. But there's a little matrix of soil material. And so water gets in there, it captures some of the water, and then it overflows down into the downspout like any other roof. But so some of the water is captured. There's also benefits to energy because you get a little more insulation on the roof. Okay? And so those plants are using that water, and then you're using it on site rather than letting it run down the street. Other things, solar panels, support of the organic gardening project, new construction, we need these green building standards to comply with now. I'm going to run out of time, aren't I? Engineers Without Borders is a cool thing that I've been doing with students. Economic scarcity, that's an interesting concept. Down here there's plenty of water, but there isn't plenty of money to clean it. Okay, that's what we call economic scarcity. So it's the outfit's called Engineers Without Borders, but it involves a lot of different students from different majors. It's not just engineers, because what we found is it's really a lot of the problem's not an engineering problem. It's a lot of other things. It's a national organization. We've been around since 2003. We've been mostly self-funded, grants. We've got some great donations from local companies and so forth. Students have ponied up money. It's a new kind of engineering. This is the old definition, solving problems or creating useful products through the application of math and science, right? Doesn't sound all that exciting. This is more what we're about. In this evolving world, a new kind of engineer is needed who can think broadly across disciplines and consider the human dimensions that are at the heart of every design challenge. And so we're trying to educate those kind of students in the real world with real constraints. This is where we work. Euro region of Honduras. It's very poor. It's mountainous, like picture at the right here. A couple of the communities have had systems that were defunct. Others have had no water system. And so when you have no water system, what do? You send the women and the children down to the local stream to fill up their buckets. And that takes a lot of time, and it keeps them out of school and doing other things that could generate economic benefit. As far as technology, it's not complicated. We know how to get rid of waterborne disease. You can bleach it with chlorine. You can use sand filters. You can even use these polyethylene bottles and put them out in the sun and maybe put them on a metal roof to improve the reflection. And you can use solar UV to remove most of the bacteria within a couple of hours' time. So a lot of this going on over in India. And we use gravity to the extent that we can because a lot of these places don't have electricity. And of course, source protection and management is important. I mean, they don't seem to make the connection that if I've got my burros and my cattle walking around by the spring, that's a problem. And so we've had to fence out, areas for them and explain to them. So key component, community participation, education, and training. I mean, that's what makes these systems work. We can go build it, design it, build it, and leave. Guaranteed it'll fail. And that's what has happened in the past in some projects. I think people now understand that that's not going to work, and so you have to have a local partner. They have to understand maintenance. They have to have the economic capability to do it. We don't have time for the movie. Sorry. Some of the students who've been involved in doing, this is our first trip down there. That was there's a little spring there. That's what we captured and piped down to a village. This is like several miles up in the mountains. Here we're surveying, it always involves surveying to lay out where this pipe route's going to go for using gravity distribution. So we do a lot of surveying work, just some of the students having fun. These are tanks that we used for sand filters for one of the villages. Okay, the organic garden. This is a collage of pictures that a friend of mine put together. What does this have to do with water? Well, I already gave you a clue on that. Here's our daily requirements. 2 to 4 liters to drink, 2,000 to 4,000 liters to produce the food that we eat, right? Isn't that interesting? Okay? So we thought, and we started this crazy thing with growing corn on the quad 2 summers ago. And I don't know if some of you saw that. We were reading this book, the freshman, new student orientation, they had to read this book called The Omnivore's Dilemma. And it was about, well, we could eat anything we want. What should we eat, right? So that's the dilemma. And there's a big section on corn and all the implications of corn, growing corn and eating corn and high fructose corn syrup and all of that. And we decided, well, what better way, and this is sort of goes along with my philosophy I told you about in the beginning, what better way to connect students to this than to grow some and eat it and see what it looks like and all that. So we did. And then we decided, well, that's not enough. We need something real. This is just a demonstration project. It's just, making a point. Let's make a garden. So that's what we did. And it's really taken off. It's up there by Metzger Field. There's 40 plots. They're all taken this year, every single one of them. People out there growing their own food. We collect water off the maintenance building up there in these 2 big tanks. Like I told you last week, we were out of water. First time that's happened, but I think we might need bigger tanks. Poorly engineered, perhaps. No, we had a limited budget. And okay, I think I'm almost done here. It's some challenges for sure. It's a lot of work. Boy, I don't keep the weeds out of my patch all summer, I'll tell you that. Go away for a week and it rains and that's trouble, right? Like next week when I go to Spain. We found that this is organic, right? Well, what do we do when you find those things eating up your tomato plants? Well, you pick them off or you figure out some way that you get rid of them without chemicals. Here, I like this one here. First the woodchucks ate the broccoli, now the zucchini. That's mom coming home all mad. Here's the little boy. His report in school, next day perhaps. My report, woodchucks, the most magnificent creatures in the world. We have those. We have rabbits. Now, about the drought, there's our spigots, right? It says stuff about conserve. Well, I went out there a couple times last week in the heat. I saw people with their hoses screwed up, on those spigots and watering their garden. I said, well, we can't have that. How can I deal with this? I could go around and confront all these people about their poor water conservation. I sat down and told my Excel student, we have the summer Excel program. This is why I love Excel. Kid says to me, why don't you just cut them off, cut the threads off? It's like, I gave him a hug. I actually gave him a hug. We went out there with a hacksaw. These are plastic, so that took 5 minutes. Boom, they're all the threads are gone. The taps are still there. Everybody has to use a watering can now, right? So we solved that problem. But it became more manually intensive.
Screw you.
Maybe we'll go with bigger tanks and put the threads back on, and people will be happier. Okay, that's my last slide. There's nothing more important than water, that's for sure. Earth has limits, and water, food, and energy are all interconnected. I hope that's something that you take away from this. And that Earth things are changing. The system is under change. Great and varied challenges for us and for future generations. I hit on some of them, certainly not near all of them. It takes a whole room of experts to talk about all of this. And finally, that we are making progress here at Lafayette. We're doing some interesting things. I'd like to see us do more. I'd like to see the entire library with a green roof on it, for example. And tanks around here that people, when the grounds people are out there irrigating the lawn, they're hooking up to the rainwater tank.
Have we been graded again since we made
Yes, I just checked the other day because I thought that might come up. We're all the way up to C+.
Where's Lehigh?
That's a good question. I'm not sure. They are building a brand new environmental studies and science or something building, so they're involved in this fight too. Okay, that's it, and I'm out of time. Thank you very much.